Welcome back. Sorry for the little bit of delay in the beginning. I got caught up with the international phone call about 10 minutes ago, which was kind of important to me, so I couldn't leave in the middle of it. My apology. So last time what we did, basically introduced the two different branches of in modern statistical science. First kind is called the descriptive statistics. Textbook definition is given here on the screen. Second one, we just briefly introduced what this inferential statistics is about, using those example of the estimating the demand equation in case of automobile sales and everything. So as a brief reminder, recap, couple of tools that people can analyze, utilize in order to bring about this descriptive statistics in practice. One of them was a stem and leaf display. Just shows what kind of underlying distribution that we deal with. Simple display of what some of those tens digits and nth digits. So easily see those distributions and frequencies and everything. Second kind, even simpler. It's a dot plot. Basically tells us the same story. And third one was a more refined one, so-called a histogram, and let us know what's the frequency of those observed values in our sample it is. Inferential statistics, it's basically try to build some bridge between some of those computed quantitative stuff like different descriptive statistics and some underlying academic theories. One of those examples could be this environmental Kuznets curve. So it's a two-dimensional picture. Control variable is a national income. The response one is the amount of air pollution. So how much pollution is being emitted per 10 year. So there's a smooth relationship between the two, and then what most prominent feature of this curve is that that's inverse U. So if you know the usual shape of quadratic function, that's like upside down. So at first it's very high, but as the value for x grows, the value for y decreases a little bit, but once the relationship passes this turning point, things basically turn around. In this case, that's the exact opposite of this. So the idea is when the nation economy starts developing, the amount of air pollution starts increasing. But once it reaches certain state of the economic development, the trend gets turned around and then it becomes suddenly negative. More and more national income basically means better and better air quality. So that's just an untested, unproven economic theory, first suggested by not Kuznets, because that's a variant of original Kuznets curve. If you look up to the original Kuznets curve, that describes the relationship between the same national income, but this dependent variable gets replaced by income inequality. So this one replaces this amount of pollution, then it becomes the original Kuznets curve. What's income inequality? You know what income is, and you know what inequality is. If you put them together, what it becomes. What's the meaning of it? Income inequality is... It's not written on my face. What's income inequality? Who cares about this income inequality? Policymakers. Why do they care about it? So that's simply the gap between the income level for the poor and the rich. But why do we care? If it's a completely capitalized system and nobody cares how much income other people make or not, but why do we care? Who cares the most about this income inequality issue? Politicians, policymakers, they care about it because their number one concern is about social welfare, not just individual well-being or utility. So for those policymakers, this is a great interest because it basically tells us at what specific level of income this gap between the poor and rich. If you imagine that this is original EKC, the Kuznets curve, the relationship gets first positive, the more and more national income basically means that the gap between the rich and poor wider and wider. But once it passes a certain critical point, the relationship basically gets turned around. Complete opposite of it. Now they replace the measure of difference between the income level for the rich and poor by this quality of air, which is typically measured by the amount of air pollutant emission. The same kind of inverse view relationship can be observed, at least in their theory. So they now want to test it because this is an unproven theory. Nobody has actually proved this theory is actually correct or not. So we have to do it. How do we do it? Of course, we turn to data, sample. That's what we do. First, gather the appropriate data set. In this case, we need two variables. First one is the rather easy to get it because that's just nothing but the per capita GDP for a certain nation. And as usual, we take log of that income in order to stabilize the process. Because if you look at the usual typical time series path of income, that's more like it. So if there's a year, and if you match that to income level, there's a clearly increasing trend because the national income account usually grows rather than decrease. So if you just simply use the raw data on this national income in order to carry out some sort of inference about the relationship like this one, the whole work is gonna break down because there's a clear linear trend. If you just keep going, the whole series gets exploded. System is not stable. So what typical people do, they first take a log and then do the first differencing. So the income level here, not just income, but that's a log of income, as opposed to log of air pollutant emission. And that's this pollution variable upon y. So there are three different things going on. First one is the solid curve in the middle of this dotted band. So this is their theory. How did I come up with this curve? I fit the model. Of course, the model is very simple. It's a quadratic or cubic model. So the underlying theory or model that we deal with is the following. Some kind of nonlinear function, but we have to specify the structure, otherwise we cannot estimate it. So the easiest way to specify it the other way. It's Monday morning. So it should be pollution. This one should be income. Is that enough? If you fit this model, will you come up with pictures like that? Obviously not. What's missing? If you want to show that there's an inverse relationship, first positive, and then it becomes negative once you pass this critical point. If you want to capture this, whether that first positive and then the negative relationship, how you should modify this simple equation? Something's missing, and that thing is quadratic term. You're missing the quadratic one. So by simply adding the third parameter, still the same logarithm, but then you square the whole thing. Then this model will do it. So you fit this model instead of the simple linear one and plot the estimation results, and that's this solid curve. So the measure of the air pollutant in the right panel of this first picture is SO2. That's sulfur dioxide something. It's a typical emission from the automobiles. The other one is a nitrogen oxide. Similar kind of gas emission, but I don't know which kind of machine they usually generate. Maybe the fossil fueling, the power plants or something like that. So some of those plants they emit the massive amount of this nitrogen oxide. So we want to measure the second measure of the air pollutant emission. X is the same, per capita GDP for a certain country, in this case is US. Because that's the data set that I happen to have. Doesn't mean that it has to be this one. You can easily replace with whatever the data you might have. Obviously, the theory is somewhat close to the truth, but you're not entirely sure that whether this model should be accepted or not. Then the way you either justify or invalidate the unproven theory is doing testing. And the testing is called inferential statistics. How do you test? You come up with so-called a confidence band. So you see that there's a solid curve in the middle of it. That's the theory. You just propose certain simple underlying economic theory and then estimate it. So that's not testing. Just simply use the data and then estimate those coefficient values and then plot it. That's this graph. But then the stuff outside is, the rest of them, you see that there's a one very thin dotted curve, just like this curve, but not exactly the same as this solid one. And then outside there's a band. So the bottom part and the top part together, if you put them together, that becomes a band. So if the theory estimated the mathematical relationship between the level of income and air pollutant emission lies completely in between this band, the theory gets accepted, but otherwise the theory gets rejected. In this case, obviously that's a rejection because this band is broken down by this part. It also breached by this solid curve by this one. And around this, the right end of this curve, also there's a slight breach of this constructed confidence band. So the theory gets rejected. But then the real question is how we can construct such the confidence band. So within the band, a certain probability level, like a 95% or 99%, we're sure that the theory is wrong or correct. In this case, it's wrong because it's not supported by the band. How do we construct it? That's of course the issue that we have to deal with the rest of the semester in this class. So it's quite early to say how to construct such a band, but at this point I just tell you that there's a certain way to, you can utilize so that you can come up with a confidence band like this one, and then once the band is constructed, you can easily compare the estimation results based on this economic theory and then reach some sort of conclusion about its the justification, whether it should be accepted or rejected. So first, the step in inferential statistics, always come up with certain economic relationship like this one. And then given this mathematical relationship, you estimate it using the sample. And then the most crucial step in conducting this inferential statistics is coming up with certain tool that you can utilize so they can either reject or accept the underlying theory. In this case, the tool that people get to utilize is so-called confidence band or confidence interval. And they specify the level of confidence, usually 95% or 95%, 95% or 90%. And I think this is a case of 95% band. So the first step is always descriptive statistics. If you want to estimate these unknown coefficients, estimate the unknown underlying economic model, you should know how to manipulate those data in hand. And that's basically coming up with some numerical guess about these unknown coefficients. That's descriptive statistics. Either the computing mean or variance or coming up with these regression estimates. But then the second step, more crucial one, is regarding the relation between the proposed theory and what the data actually tell us, is building the confidence band in this case to carry out the testing of those proposed theory, whatever and whoever you talked and discussed the issues with. Yeah, it's just one example. I mean, you don't ever get to construct a band or anything in this class. So just telling you that what's the main criteria people use to differentiate so-called descriptive statistics and inferential statistics in practice. And then we went on. Well, not we actually didn't went on. We have to do it now. So starting with the discrete statistics, the major location plays a critical role. So this one basically tells us where the center value for certain underlying distribution. So distribution can take any functional form, literally any. So one variable, say x, might have the distribution function like this. Second variable y might be a lot smoother, like that. So whatever type of or shape of underlying distribution you might deal with, there's always what's called a center value. So if you just look at the middle of this distribution, where is this center? And similarly for the second distribution, it's easier to pick up that location because it's very smooth and symmetric. So the so-called measure of location basically tell us what these numbers are. What's the number for this distribution A, that for x, and what's that for this second distribution y. And two simple measures of that location. Where is the middle value of this the sampling distribution or population distribution of these variables? First one is by far the most important was sample mean, and second one related but not quite the same, median. Definition of sample mean cannot be simpler. You just given n different observations of certain random variable x, add them all up, and then divide the sum by its sample size, which is little m. So notation wise, we get to use this summation more than 100 times in this class. It's better, have a clear understanding of what this notation means. So if you see this big sigma, whenever and wherever in this class, it just means sum. Given these n different values, you just add them all up. And then given this sum, which is a summation of this x sub I, you get to divide the whole quantity by its number, which is n. That's the sample mean. Other people simply call that as average. I'm pretty sure that there are other names as well. If you expand the summation notation and simply use this bracket, that's basically nothing but this. x1 plus x2 plus all the way to the last x, which is xn. Sum them all up and then divide the sum by its sample size, which is n. So that's how you compute the sample mean. You should all know it. So example. Say that there was a test and 8 students took it, and the possible max score that one could receive out of that exam was 100. And distribution is here. It's not particularly in the rank of in terms of its size. It's just a random order. First guy received 35 out of 100. Second guy 20, and so on until you see this last guy who scored the minimum score, which was 11. Sample mean, just add these 8 numbers up, which is going to be 280, and then divide the sum by its size, which is 8, because 8 people took it. So the average is 35, or 35%. But if you see the potential effect is of outlier, now you assume that you keep the first 7 numbers same, you keep these 7 numbers, but then replace this last one of 11 by 71 by simple mistake. So that's not intentional. The recorder somehow the mistakenly replaced this 11 by 71 so that the sample mean gets to increase because this 71 is 60 bigger than the first entry with real entry, which is 11. So you keep the sum of the previous 7, which is sum of this 35, 20 all the way to 39, which is the second last one. So that's 269. Simply replace this last entry 11 by 71 because number 7 and number 1 might look a lot like to each other to some people, although it's not to me. And then the new sum is going to be 340 instead of 280 if the computation was correct. It's obvious because the difference between the true value and then the mistaken recorded one, which is 71, the difference is 60. The sum must be 60 bigger than the previous sum, which was 280. Still divide the sum by the same sample size, which is 8, and then you end up with a wrong mean of 42.5. So obviously there's an increase. It's a huge increase actually. Previously it was correctly computed as 35, but now because of this wrong addition, the wrong replacement of the previous 11 by 71, newly computed the sample mean is now 42.5. So there's obviously a certain percent increase, and that in this case happens to be 22. How do you get this number, 22? Where did I get this number, 22? So previous average, if it's correctly computed, that's 35. But because of this mistake that was introduced, 11 is now replaced by 71. Obviously the sample mean is going to be different, and that one in this case 42.5. But then we claim that the unexpected increase in the sample mean because of this recording mistake happens to be 22%. How do I know this is 22? Well, I know that it's a Monday morning. Wake up. How do you compute this 22% increase thing? Divide which one by what?
7 is difference between 42.
Yeah, this one.
Minus 35%.
Yep.
And divide by 35.
Yeah, exactly. So always, if you want to compute the percent change, first figure out what the difference is, the difference between the previous value, which is 35, now the subsequent new one, which is at 42.5. So the difference is going to be what, 7.5, and then you just divide it by the previous value, which was 35, and you'll get this 22% thing. So obviously this is a big increase. So what does this exercise tell us? Why do we do this simple exercise? What's the lesson? Of course. So true in general in life, but in this class, why do we do it? What is this 71? What's the name for this guy? Outlier. So we want to see the effect of outlier in computing sample mean. So outlier can have a big impact or small impact? Big impact on the sample mean. So that's the lesson. So we of course use the sample mean as a reliable measure of the location parameter in any sort of like a parametric distribution. But if there are outliers, the example that we talked about last time, you want to figure out the average income of all the citizens who reside in the city of Seattle. If you mistakenly include that of Bill Gates in your sample, they usually distort the whole distribution toward the right end. So it shows to give more specific example of what kind of impact of this outlier thing can have in computing the sample mean and everything. So it's a still good measure, most reliable measure of the central value for any sort of distribution, but you have to be a little bit careful in analyzing or understanding what is the value for the sample mean really represent, and that's one of the things that you have to keep in mind is that it can be easily affected, and quite a big deal, by those existence of outliers, either big or small values in your sample. In order to mitigate or make that problem a little less serious in practice, people came up with this idea of a median. It basically does the same job of letting us know where the central value of that certain distribution is, but in slightly different way. So median is certain quantity as defined as this one, literally middle value, if and only if the size of sample is odd number, like a 3 or 7 or 11. You know what odd numbers are. 1, 7, 5, and 3, all those numbers are odd. For the rest of them, you have to consider what are those two values in the middle of the distribution and simply take the average of those two. So the critical point that you have to keep in mind in computing or figuring out the median of certain distribution, first have to figure out whether the sample size is odd or even. If it's odd, so very simple. So first rank those observations. Could be 3, 10, or 100. So numbers are odd because you only deal with 3 entries, and the one in the middle is obviously this one. So that's the median. But if you deal with instead of 4, say that there's a 200. So now the number becomes even suddenly. But then you see that in the middle, there are 2 different numbers. You can't really tell which one is in the middle because they're both of them. So in this case, you have to take the average of these two. That becomes your median. So the first thing you have to think of when you are asked to compute the median of the certain sample, figure out what's the sample size. Is it odd or even? If it's odd, job is simple. First, simply rank them in terms of its size. Figure out the one in the middle, and that's going to be your median. If the number turns out to be even, so your job gets a little bit more complicated. First, rank them in terms of its size. Figure out those two in the middle of them, just like this one. So without any mistake introduced, the 8 score distribution was this one. Starting with the smallest one, you rank them first in terms of its size. Second smallest one of 20 goes up to 35 and all the way to the largest entry of 50. So it's obviously you deal with the even number of the sample points, which is 8. So there should be 2 in the middle of them, which is 38 and 39. Median of this distribution is average of those two, which is 38.5. Now you repeat the same sort of computation when you introduce this the unintentional mistake. 11 now disappears, and now there's a wrong number, 71 appears. Just like the same sort of exercise that we did in computing the sample mean. Otherwise the same. Now those two values in the middle of this distribution, one of them changes. Previously it was 38 and 39, but because of this the drop, you just drop this lowest one and then add this wrong number of 71. The two middle values, 39 you keep it, but instead of 38, 42 becomes the other value in the middle of this distribution. So now you have to take the average of these two, 39 and 42 instead of 38, and newly computed median in this case happens to be 40.5. So still increases, but a lot less compared to the previous case of computing the sample mean. Now the percent increase is only about 5.2%, which shows impact of these potential outliers in your sample. In the case of computation median is a lot less compared to that of the sample mean. That's the whole point. Okay. Questions so far? No questions. All right. Oh, by the way, the first problem set is on the website, so you can start working on it. By the end of today's class, I don't know, you can finish about half of it. But certainly when we finish the stuff tomorrow when we come back, you should be able to handle all of those 5 questions. And then the first quiz, it's either next week or the one after. Likely next week, I think. Next Tuesday. So let's fix it actually. Quiz number 1. It's going to be at the end of class. And I'll give you about 15 minutes, or 20 if you need more. So I'd say about 15 minutes. It's just one question, should be enough. So you all know how the quiz is going to be done in this class. I explained it like twice or something. So there are 5 questions on the first problem set. Solutions will be posted sometime this week. I guess that either Wednesday or Thursday. So exact model solutions to those posted problem sets will be available in the class website. You can download them exactly the same way you did the problem set. And then just go over them carefully and try to understand all of those. And I'll just draw one of those 5, slightly change the numbers, or slightly change the structure, and then put that on the quiz, and you just get to do work on it when you come back next Tuesday. And that will be done in the last 15 minutes of the lecture, because I cannot do it in the first, because if I do the quizzes first and then do the lecture, people will leave in the middle of it. So I better keep you rather than let you go. It's just one question. You don't really. And then we'll repeat it like 4 more times. So 5 quizzes, each of which is worth like 4 points out of 100. So quiz is 20%, because there will be 5 of them. So that was that. A few remarks. Like we said, median value is less affected by the existence of outlier than the sample mean, as we saw clearly from these 2 examples, numerical examples. And furthermore, either decreasing the first 3 in this case, so first 3 other than those 2 values in the middle, these 3, and largest 3, those 3 in the exact opposite side of the spectrum, these 3, have nothing to do with the median. Doesn't matter whether you replace this 71 by 71 billion or 100 million or something, still the median, the average of these 2. Same thing, whether you replace the 20 by negative million or negative billion doesn't make any difference in terms of this computing median, because you only take care of those 2 in the middle of this distribution. Don't even look at what those numerical values for on the left hand side and what are those on this right end of it. Doesn't matter. So it's completely free of those potential big outliers or small outliers. It shows literally how robust this measure of location, median, can be to the potential outliers in the sample. But obviously, if you consider the mean, whatever comes in here, or what number you put on the left hand side, clearly makes a difference, because you have to sum all these numbers first. So the way we compute the mean, add all those entries. So by adding all of them, you certainly introduce some sort of difference. By adding the big one or adding small one on the other side, so that certainly gets affected by those huge or small numbers that you are adding up, but that's not quite the case in the case of median, because you don't even consider those. So it shows why this median measure of the middle value can be robust to those potential outliers. Okay. Now, that was the measure of location, center value. Different kind of measure sometimes tell us a lot of information about the underlying distribution. One of them is variability. This one, like we said before, simply tell us how much spread that we are having in certain distribution. So 2 examples that we introduced last time was this one. So these are 2 different distributions. Distribution A and distribution B. Middle value, whether it's measured by mean or median, just about the same. It's right here. It's pretty much the same for the population. Distribution A and distribution B. But amount of spread is quite different. The second distribution, this guy is a lot more spread, because it's a lot more squashed out. So we want to measure it. We want to quantify it. What's the exact measure or amount of spread that we are dealing with in each distribution? And that's sometimes done by so-called the range. Other times it's done by so-called sample variance, far more important than the first one. Very high chances that this sample variance will be discussed during the quiz. So what's range? Very simple. you come up with the rank of those distributions that you have. Smallest one typically denoted by x sub 1 because it comes first if you rank them in terms of its size. And largest one, x sub n, because it comes last. How do you compute the range of the distribution? Simple. Take the difference between the largest value and then the smallest one. That's range. Subtract the minimum value from the max one. So that's what's the range is. Advantage of using this one as the measure of the spread, variability, is obviously computation is very simple. You just locate where the mean value and max value is and just simply subtract the mean from the max. That's it. Downside of this one is written here. Doesn't care about all those numbers in the middle of them. You only take account of those mean value and max value. No matter what happens in between, you don't care. That's not good because you are basically throwing away all that valuable information. So what I'm saying is, so minimum value could be like a 2. Max value could be like 100, like a test score or something. Like a bunch of people in the middle of this. So in one case, the distribution can be very even out. So you have somebody here, someone here, or just evenly distributed along this axis. But in the second case, although each endpoint are still the same, it could be a lot more concentrated, only in the middle of them. Intuitively, which one's got more spread? So that's a possible distribution A, and that's a possible distribution B. Intuitively, which one's got more spread? This one. But in terms of range, what's the measure? Same 98, so that's not good. If the measure is reliable, it should represent the true meaning or measure of the spread in the sample, but range clearly doesn't do that. So that's about the downside. Advantage, big advantage, disadvantage of this range. So if this is indeed the case, what do you usually have to do first? Instead of computing range, the very first thing that you might want to try with these samples like this one is see whether there are outliers. So these could be simply outliers, not good measure or representation of the sample. So you go through some sort of test, a simple test, to determine whether indeed those values that appear to be outliers are indeed outliers. And if the test result says that they are indeed outliers, you kill them, throw them away, and then you get to work on this rest of numbers. That's the better approach. So all I'm saying is that the range is easy to compute. It's still one measure of how much variability that you might sample have. But clear downside of this measure, in the case of potential outliers, this one can distort the whole story, the real storyline of this amount of spread or variation in your sample. Can misrepresent the true story. So you should be careful using this one. A better measure of the amount of variation or spread is the sample variance. By far more important and more widely and more frequently used than the range. I've never used range in the practice, but sample variance you compute and use it all the time. First, definition. So definition is a little bit messy. You first have to compute the median, not the median, sample mean. So if you write down certain letter or character, say y, and then you put bar on top of it, that means the sample mean. You must have seen it before. So the first step in computing the sample variance is you have to first compute the sample mean of so x bar. So that's the sample mean for all those observations for x sample. subtract the computed sample mean from each observation xi, so there should be as many as n different differences. So the way you do it, see the first value for x, which is x1, subtract the computed sample mean from that first entry, and keep it, and that's the first deviation. We call that as deviation, difference. Repeat the same thing for the second entry. So now you take the second x, which is x2, subtract the same sample mean, and keep the deviation, second deviation, and you basically repeat the whole procedure for the rest of those sample points. And it should be naturally n different deviations because your sample size is n. The critical step is now you have to square them. Don't forget to square it, because if you don't square, something not good happens. So square them. Still there are n different squared values of those deviations, n different deviations. Now you sum them, and then divide the entire sum by sample size minus 1. That's another crucial step. So a lot of people make mistake on exams or quizzes. Forget to divide the sum by sample size minus 1, and they just simply divide it by sample size n. And to simplify the summation, in practice people sometimes use this notation of big S sub big X and X. But whenever we introduce this notation, I'll define it first. So that measures reliably how much spread or variation you have in your sample. But then the next pure question you might have, how come we have divided this sum of square values by sample size n minus 1 instead of just simply n? Does anybody know why? So it's natural to divide this quantity by n, but why do we have to subtract 1 from it? Because you want to? Does anybody know why? Why n minus 1 instead of n?
If there's only one value, there's no meaning, so just minus 1.
Well, that makes sense. I never thought of it that way, though. Yeah, only one sample. I mean, there's no variation. It's just very smart. But that's not what I have in mind. The reason is because of what's called a bias. We'll get to define this when this class gets like in the middle of May or something. If we don't subtract 1 from sample size and simply divide the sum of the square deviation by sample size, the computed quantity will have a property called a bias. That's not good. So you want to kill this bias thing. And the easy way to fix the problem is subtracting this 1 magically. So if you divide this quantity by n minus 1 instead of n, the whole quantity computed sample variance is a bias free. So that's the reason. And you want to ask what the bias is, and of course I can answer it at this point, but you probably won't understand what I'm saying. So I'm going to delay the answer until we get to deal with this bias thing officially, sometime in the middle of May. And then the whole question will be brought back to literally show how this subtracting 1 from the sample size can fix the so-called bias then. So don't worry about it. And another familiar quantity, after you compute this sample variance, you might want to take the square root of it, and that becomes so-called sample standard deviation. They basically do the same thing, although the sample sample standard deviation is a little bit lower than the computed sample variance in most cases. And this one, actually both of them, has to be always positive, because we cannot even define negative amount of spread. Amount of spread is always positive. If the amount of spread is 0, what's that? When do we have a 0 standard deviation? So imagine a certain case where the computed sample standard deviation is 0, or sample variance is 0. When would that be? So you go ahead and compute this number, s squared. Then you see that the computed number is 0. When does that happen? Yeah, when is that? Yeah, identical distribution, identical values, like a 3, 3, 3 all the way, or 1, 1, 1, 1 all the way. Might happen, but like a gender, like the person's gender, either man or woman. If it's a man, you assign 1, or if it's a female, you assign number 0. But if you stop by one of those engineering courses or something, pretty much 1, 1, 1, 1. Or back in the 90s, when I was a college student in Korea, so it was electronic engineering. So I think class size was like over 100, but there were 2 female students in it. So got lots of attention whenever they enter the class. So it happens. I mean, it's still different observations, but numerical values are exactly the same. Middle value is just the same as the observed value, but the measure of the spread, variance is going to be obviously 0 because there's no spread. It's just, at one fixed point. You just get repeated, observe it repeatedly. Couple of important properties of this standard deviation and variance. First one, unit of this computed sample standard deviation happens to be the same as the unit of the original x. You know what unit is? If you measure certain height, somebody's height, it's either centimeter or meter or feet or inch, depending on different metric, that's unit. Or if you measure distance, sometimes the unit is kilometer, some other times it's mile, so depending on what metric you want to use. So that's a unit. So there must be some unit for this original x, your sample, but then this first statement claims that the unit of the computed s, square root of this sample variance, exactly the same as that of x, y. So there's a unit for this x, and then if you compute the sample variance first, and then compute the sample standard deviation, first statement tells us that the unit of the standard deviation, unit of this s thing, must be identical to that of this x, because how come the units are the same? What's the unit of this s squared? Let's do that first. So say that this is like a distance of commuting. So you guys commute between home and school every day. So if you commute like 5 miles, that's 5 for you. And if that number is 20 miles for the second guy, the second entry is 20. If x's are those distances measured in miles, what's the unit of this s squared? X is measured in mile. Unit of s squared is mile squared. Then what's the unit of s? Take the square root of it. Mile. Same. So first the square term, so the unit becomes unit squared, but then you take the square root of it, so you basically bring it back down to the original unit, which is mile in this case. So that's why those two things are the same. Second one, more interesting one. Whatever the sample you might have, you can easily compute the sample mean, and then you figure out those each different deviations from those sample point, subtract the sample mean from the first x, have that, subtract the same sample mean from the second x, and secure that, and repeat it all the way to the last x, which is xn, and then subtract the same sample mean from that x. If you add up all those different deviations, difference between the sample point and the sample mean, they necessarily add up to 0. So that's why we have to square it. So the reason why you have to square this, if you forget to square it, the whole sum becomes 0, which just basically means that there's no sample spread or variation in this sample. How do you show it? So intuitively that's very much like, because what's basically saying, you might have certain distribution like 10 different points. If you compute the average of these 10 different numbers, they will be pretty much like this one, right? Because that's average. So deviation basically measures this difference between this first entry and then this sample mean, difference between the same sample mean and the second entry, and difference between the third entry and the sample mean, and then you just repeat it. So these 5 line segments on top of this horizontal one, they are positive. These are positive numbers because this one's bigger than that. Right? But those 5 underneath, they must be negative because you're subtracting something big from something small. So this is negative, that's negative, that's negative. So you have 5 positive numbers with different length, and another 5 different negative numbers this time with different lengths. So this statement is saying that basically if you add up all these 10 different numbers, these different numbers, they add up to 0. They look like. Because they are different in signs. 5 of them positive, the rest of them are negative. So they might be actually indeed add up to 0. But you have to show it analytically this time. So how do you show it? So how do you prove this claim? Well, if you know how to do it and don't want to say it, that's okay. But if you don't know how to do it and don't say anything, that's not good. So what's the first step if you want to show it? Well, the first step is write it out. That's the first step. Write out the question. So index runs from first one to the last one. There's a sample point. And the computed sample mean, and you want to show that that's 0. What should come here? What's the second step? First step was writing it down. Second step is just looking at it. What do you do with this? You distribute the summation. So this one is just a coefficient. So if you know the math, simple algebra, you can distribute these numbers to each entry inside the bracket. Right. So it's a distributive law or law of algebra. You can do the same thing with the summation. So apply this one to the first entry inside the bracket and then repeat it to the second one. That's this. Repeat the first one down here, but then we can rewrite this. What's that? Why? So if you rewrite it, that's what you're saying, right? How do you know it? What's the difference between this guy and that guy? You see the index I here? So you cannot pull this one out because this one is bounded by this index I. But there's no index. It's completely free of it. So if you imagine what the summation of 1, that's basically saying 1 plus 1 plus all the way to the nth one. So n times. So basically n times 1. And the reason is because this sum n is completely free of this index. You can just pull this one out. Rest of them is just n. So if you apply the same thing to this one, this guy is completely free of I, so you can pull it out. But then inside what's remaining is just simply n 1 plus 1 plus. You just repeat it n different times, which is n. But then use the definition of the sample mean. Because we defined it. It's nothing but the definition of this sample mean. So there is a sample mean, and we defined it as this. But then you see that the n outside and the 1 over n inside, and these two cancel each other, and what's remaining is exactly the same as the first. So that's a 0. Very simple illustration. And for any sort of mathematical proof, you start by stating the statement that you want to prove, and then you end it with the 3 letters. Q dot, E dot, D dot. That's the end of any valid mathematical proofs. Meaning, anybody, the math major here? What's Q dot, E dot, D dot? Quite easily done. That's a joke. It's some Latin. So the ancient Rome. Was some meaning like valid, justify something. It's a Latin. You know what Latin is? Ancient Italian. So famous mathematicians who studied the developing these systematic tools for mathematical proofs are all Italians. So they came up with these initials. So it's a scientific, justifiable something, I've forgotten. I learned it more than 10 years back, but simple, people just simply joke it as a quite easily done. Third remark, because of this second property, second remark that we just proved, it really tells us that once we know the n-1 different deviations of these different sample points, because we do know that they necessarily sum up to 0, the last deviation, which is the last entry minus the same sample mean, can be easily found. So what it says is, so you think of the 3 numbers. Right? Last one is not known. So you have 3 numbers. You do know that sum of them is 0. Just like this one. So what basically this last statement is saying, even if you don't directly observe the value for the last entry here, right in the middle, no, not right, sit in the middle. So 3, 5, and x. Unfortunately, we don't observe this last entry x, but we do know that the sum, they add up to 0. But then using these 2 facts, we can easily restore this value for x. That's what's saying. Because you do know the sum. So what we really need to know, not all those sample points, but sample size -1. As long as we have observations for n-1 entries, that's good enough. You can easily compute the last unobserved one using this property. And for that reason, the number n-1 is called the degree of freedom. It let us know how much freedom, or what degree of freedom that we can enjoy. And that's as much as this number n-1, because as long as we have this entry, as long as we know or see the values of first n-1 sample points, that's good enough. It basically tells us everything about that sample distribution or the sample. And this terminology, degree of freedom, when you get to take the sequel of this class, which is the Introduction to Econometrics, either in the second semester or next year, will play a very critical role in many different places. So it's not a bad idea to familiarize yourself a little bit with this terminology, degree of freedom, now rather than later. So those are the three rather interesting remarks. Now we move on. Some useful mathematical fact when it comes down to computation of the sample variance thing is the following. So we define the sum of those square deviations, and notation wise this big S sub double axis, which was introduced here. So it was defined back here when we were defining the sample variance thing. So you see the numerator of this fraction defined by this quantity. And regarding this quantity, we can show some interesting property of that, and that's this. So first compute the sample mean and subtract the computed sample mean from each sample point, which is x sub I. Square the deviations and sum them all up, and we can easily show that this summation is nothing but the difference between just the sum of x squared and sample size times square value of those computed sample mean. So the middle part you have to figure it out, and how you show it through these steps. First, expand this the quadratic a plus b. If you square the sum, that's a squared plus b plus twice a times b. So just apply the usual formula for here to here. Then if you expand it, the first term that in the second line is going to be xi squared, square value for those each sample points, twice the first entry times the second entry, which is sample mean and then each sample point. And the third one is obviously the square the sample average, sample mean. And like we did before, using the distributive property of this summation, you can distribute this summation sign to each one of these three terms inside the bracket. And then the first sum is going to be summation of those first entry, which is xi squared. And second summation is the summation of the second entry. But we do know that this twice sample mean is completely free of this index I, so you can pull it outside the sum and write it as twice sample mean and multiplied by the sum of all those different x's. And then similarly distribute the summation to the last entry, which is square the sample mean. Right? For the first term, there's not much we can do it, so you just copy it down here. But then the second term here, the sum of those different x's can be rewritten as n times sample mean, right? So you define the sample mean as 1 over n times sum of all those different x's. So if you move this n to the left hand side, that's n times sample mean sum of all these different x's. Talk about this one. So you see that the summation here, and then you replace this right hand side sum of x by this n times sample mean of it. Then you have twice n times x bar sample mean of x squared, because you already have another sample mean to the left of it. For the last sum, we again apply the property that the sum end sample mean squared is completely free of I, so you can pull it outside and then just multiply by number n, because that's this top one. That's number of entries that you're having for this sum. But then obviously one of these n times sample mean squared and then the last term n times sample mean squared, they kill each other because signs are different. Here it's a negative, here it's positive, but then still one of them remains, and you have this finally desired outcome. Okay. Where do we use it? Where do we use this formula? Of course, in computing sample variance. Compare these two different definitions. So go back to the definition of sample mean. I know that's boring. That's the way it is. If whatever subject you first get into, you put up with the boring part and then fun part comes along. But then you have to get stuck with that boring part for at least like 1 or 2 years. In my case, 4 years. And then a little bit of fun part came like a year or 2, and then even more boring part follows. So you're in the beginning of that boring stuff now. Feel sorry for that, but that's the way it is. I mean, college education, most part is quite boring. Huh? If you want to have more fun, why don't you get a job right out of high school or something? But there's certain value to it if you just continue it. I mean, 20 years from now, you don't want to sell at the McDonald's or something. I mean, no offense to those people who work at McDonald's, but you know, different values. I mean, some people value their future job and a lot of more important things down the road. But to some other people, present value, the income and lifestyle or other things that you value more is certainly important than those what's ahead. So getting back to the discussion of why we have to compute this, why we have to figure out this simple formula is because of the following. So standard deviation or sample variance is defined as that. So you want to should be red. So that's S squared. You want to compute this quantity. So that's the case that you follow the definition. But if you, so actually these are the same. But if you use the proven formula, which is this one, that's nothing but same n minus 1. But this time you do this instead. Right? So all I'm doing is just replace this summation in the definition by the result of this derivation. Right? Because of this formula, these two quantities must be exactly the same. So it's just a question ahead. We want to compute the sample variance or sample standard deviation, but knowing that these are the exact same quantities, doesn't matter which way you compute it, you either use this formula or that formula. But which one's easier to compute? Probably this one. Yeah? So if you have like 5 numbers, doesn't matter. So the difference is not that much. But if you have like 20, so the computer will do the computation. But if you have to use your hand, probably this one is easier to compute. Because for this one, you first have to compute the sample mean and come up with those n different sample point deviations, square them and then sum, and then divide the whole thing by n minus 1. But down here, you just simply square those sample points and then sum them up, and then subtract the computed sample mean squared and times n, and then divide the whole thing by n minus 1. But both ways, you still have to do some work, but if you have to choose between the two, obviously the second route delivers you the same answer in simpler and easier way. So that's the whole reason why you had to show this formula, nothing more. I stop here unless you have any other questions. So when we come back tomorrow, we start with this proposition 1 and show it together, figure out how these facts can be proven, and then I'll try to relate those to some of those homework questions so that I can help you with those upcoming quiz or anything. Thank you.